Welcome to the Explainer. Today, we are diving into a totally revolutionary way to see the unseen. We're talking about a technique that uses color to reveal the secret stresses hidden deep inside materials, right down at the atomic level. So, let's get into it. Here's our roadmap for today. First, we'll tackle the fundamental challenge of trying to see these invisible forces. Then, we'll look at the classic tools scientists have been using for decades. After that, we'll see how a digital upgrade adds a whole new, powerful dimension of information. We'll learn to decode what all these new colors mean, explore what this new vision can actually do, and finally, I'll show you how you can try out this virtual microscope for yourself. So, let's dive right into the core problem. We're working with materials at a scale that is just, well, it's almost impossible to wrap your head around. I mean, really think about that for a second. How on earth can you spot a flaw in something you can't even see? This isn't just some academic thought experiment. It's one of the single biggest hurdles in all of materials science. You see, at this level, a single atom out of place, or just a tiny bit of stretching in a crystal, can be the difference between a breakthrough new technology and a total dud. The big problem is that these forces, these strains, are basically ghosts. They are completely invisible to even the most powerful conventional microscopes. You know something's going on, but you just can't see it. So, how have scientists tried to get around this in the past? Well, they've relied on a really clever and powerful technique that's been a cornerstone of microscopy for a long, long time. It's called optical darkfield imaging. And the idea is pretty cool. Instead of looking at the light that passes straight through a sample, scientists look at the light, or in this case, electrons, that get scattered off of it. This makes the thing you're interested in shine like a star against a pitch-black background, revealing all sorts of features you'd otherwise totally miss. So when electrons pass through a crystal, they create this really complex scatter pattern. Darkfield imaging is kind of like digitally reaching in, grabbing just one of those scattered beams, and then tracing it backward to figure out precisely which atoms created it. It's a fantastic tool for sure, but it only tells you part of the story. So, how do we take that classic idea and give it a massive 21st century upgrade? This is where things get really exciting. We're talking about using digital processing to unlock a whole new layer of information. And this comparison just lays it all out perfectly. Traditional dark field is great. It tells you where a particular crystal structure is. But this new digital method, it tells you where it is and how that structure is being stretched or compressed or twisted. It does this by capturing something called phase information, which is totally invisible in the old method, and then it translates that hidden data into a full spectrum of color. And the process itself is, surprisingly elegant. You start with your standard electron microscope image. Then, a computer generates the diffraction pattern, that scatter we talked about. Next, you just digitally select one single spot from that pattern, and finally, bam! The software reconstructs the original image, but now it's infused with all this vibrant color that carries that hidden phase information. Okay, so what do all these new, wild colors actually mean? It's really like learning to read a new language, where every single hue and every shift tells you a story about the forces that are at play. The researchers behind this technique use an absolutely wonderful analogy to explain it. They say the patterns that appear are like the beats you hear when you're tuning two musical instruments. When the notes are just slightly out of sync, you hear that pulsing wah, wah, wah sound. Well, the colored stripes in these images, they're the visual equivalent of that. These color bands are called interference stripes. They show up wherever there is a slight mismatch or a strain in the crystal's perfectly repeating atomic pattern. Just as musical beats tell you two notes are out of tune, these color beats are telling you the atomic lattice is being pulled or pushed out of its perfect shape. And this right here, this is the most important takeaway of all. The absolute color in any one spot doesn't really matter that much. What matters, what contains all the information, is the change in color from one area to the next. If you see a big, solid block of uniform color, you're looking at a perfect unstrained crystal. But the second you see those colors start to shift and form these gradients or stripes, you know you found hidden stress. Okay, so now let's see how this all builds into some incredible real-world applications. Because this isn't just a neat visual trick, it's a tool that is solving real problems right now. The sensitivity here is just staggering. I mean, we are talking about detecting shifts on the scale of picometers. That's a trillionth of a meter. The researchers actually compare its precision to the LIGO observatory that detects gravitational waves. So instead of sensing ripples in space-time, this technique is sensing ripples in the very atomic fabric of a material. It's incredible. So what can you do with that kind of power? Well, you can pinpoint the exact location and type of a single atomic flaw in a crystal. You can map out the precise stress points in advanced semiconductors, which is absolutely critical for designing next-gen computer chips. You can pick out individual nanocrystals, visualize quantum dots, and even figure out the exact 3D orientation of a crystal from a flat 2D image. It's a massive leap in what's possible. And here's the best part. This isn't just some theoretical concept locked away in a research lab. The creators have made this technology accessible in a way that is just truly remarkable. Because all the calculations are so fast, this whole thing can be done live. A scientist operating an electron microscope can literally see these color maps appearing in real time. It gives them instant visual feedback on the atomic level forces inside their sample. It turns a static image into a dynamic, living dashboard of information. And they've gone one step further. The researchers have actually built an online simulator that anyone can use. You can go to their website and play with this digital darkfield technique yourself, getting a real feel for how it works without needing access to a multi-million-dollar microscope. It's fantastic. And all this leaves us with a fascinating final thought. We've just seen how translating a hidden property, in this case phase, into color can reveal the entire invisible world of atomic strain. It really makes you wonder, what other invisible worlds in biology or chemistry or even astronomy are just waiting out there for us to find the right way to color them in?